The exploding eye. Now, most lectures that we give before audiences focus on pathology. You see a patient, you look at findings, you try to explain it, you write an article, give a presentation. But I thought we could do some back-to-the-bench experimentation. And so what I did was I ordered a big bag of pig eyes online. It's amazing what you can get online. And we're going to subject these pig eyes to various amounts of trauma. We'll start by lighting them on fire, subjecting them to heat injury. And then we're going to take these pig eyes and subject them to various chemicals, acids and bases, and we're going to see what happens to these eyes over time. Then we're going to basically use various projectiles, BB guns, airsoft, paintball, and we're going to shoot these pig eyes and see how they react to various trauma. Then I've got some high-powered industrial lasers that I ordered from Hong Kong, and we're going to shoot some lasers at these pig eyes, and we're going to see what happens. And finally, I went to the local fireworks store, and we'll try various explosive devices on these eyes. Now, the point is not to be entertaining. Well, hopefully it is, but the point is not to be entertaining, but to give us a little bit better example of how the eye works, some of the trauma that our patients can experience out in the wild, so that we have a better sense on how to treat these people. So let's begin. We'll begin with heat and fire injury. Now, it's interesting. The eye is a very sensitive structure, and yet very rarely do we ever see heat-fire injuries. It's amazing what you can do with WD-40. But, I trained at a hospital, a very large one, that had a burn facility in it, and yet I was very rarely ever called to see eye burns. And the reason why is that the eye is protected by the skull from pretty much all direction from most trauma, including heat. It also helps that the eye is full of water. If you take a balloon and hold it over a flame, it's going to pop almost instantly. But put some water in that balloon, you can hold it over a fire, and it doesn't pop. And why is that? The reason is because water is a great conductor of heat. It conducts heat away from that area. And even though it looks charred, that's actually just soot from the candle. The balloon is relatively well protected. It also helps that the eye is covered by a thin layer of tears. And that tear can quench small flames, which explains why you can put out a fire with your fingers if necessary. So a couple of protective mechanisms for heat injuries. But we do see some on occasion, so let's go over them. Cigarette burns is one of the things I see every once in a while. Now, it's been maybe a decade since I've been over at Disney World, but the last time I was there was very early in my eye training, and I found myself, you focus on what you think about all the time. You guys probably look at eyes all the time. I was terrified walking around Disney World because there were all these tourists, Europeans, that had cigarettes held at waist level, waving them around, and children running around at the same height, eye height. And so I was constantly paranoid that a child was going to run into a cigarette. And we do see that on occasion, but not as much as you would think. The interesting thing about cigarettes is they burn hot, but it's a mild flame. I mean, you can put it out if you do it fast enough on your hand without hurting yourself. In fact, you can even put it out on your tongue if you're of that sort. And the tongue is covered by a thin layer of tears, which helps. So if we put a cigarette out on a pig eye and wash this off, surprisingly very little damage. And this seems to correlate with what I've seen in the office. Usually a young child brings in, the parents or the grandparents are extremely embarrassed, really nervous, the kid's crying, they've got junk in their eye, but for the most part, very few bad injuries from cigarettes. Have you guys ever seen an electronic cigarette? I ordered one. I don't smoke. I just ordered one just to see what they look like. Basically, it has a battery component to it. The nicotine is in this end. You inhale through this end, and the other end has a sort of a plastic simulated flame or char. And doesn't hurt at all. No burn injury. If you need another reason not to smoke, there it is. All right, sparkler injuries are a little bit more intense. Sparklers are dangerous, not so much because they're flame, but because they burn so hot. And they burn hot because they're made of magnesium. And magnesium is the same stuff that's in this magnesium fire starters that you scrape off that campers sometimes use. Magnesium burns at 4,000 degrees, extremely hot. And this is a strip of magnesium I'm dipping in water. And you can see that it doesn't really quench with water quite as well as you would expect. I mean, it takes a lot to put out a magnesium fire. So here's some sparklers. Now, the sparkler will go out if you put it in water, but it takes a couple of seconds to go out. And so here we go. So it burns out. So it will burn out, but the tear film has very little chance to put a sparkler fire out if it's jabbed in the eye. As you can see here, some significant burn trauma. And surprisingly, I do see these injuries on occasion. It's usually in a young child, 18 months, held in the hand. Someone holds a kid a sparkler, and then they jab themselves in the eye because they're kind of uncontrolled anyway. And it usually looks something like this. The sharp end goes up underneath the eyelid because it doesn't usually puncture. And then they get all this junk in their eye and a big abrasion and maybe a small burn. And it requires, Morgan lenses and washing out. It gets crying. It's ER. It's just a mess. Fortunately, I haven't seen many burns that were terrible from this because it's usually momentarily, but it's something to be aware of. So sparklers are dangerous. The third heat injury we see is the curling iron, which happens on occasion. Curling irons can actually go to very high temperature. This one is set for about, 430 to 450 degrees. And if you think about it, that's the same temperature as your oven if you're making a pizza. So imagine that oven grill touching the eye. And so it can cause some significant burns. But fortunately, once again, this is usually a glancing burn across the eye. And even though it's hot, don't usually see as much damage as one might expect. This is not a burn patient, but this is what I see. It usually looks like a linear, whitish, hazy cornea. It's dehydrated a little bit from the heat, and so it's a little bit thinner. You hydrate, pain control, antibiotics, and most of the cases, fortunately, that I've seen have done quite well afterwards. But a heating iron. Our take-home point with this, though, is that burn injuries, rare, and at least in my experience, they don't cause significant trauma if they're mild. Our next topic, projectile eye injuries. Now, I thought about talking about handguns and rifles, but it's pretty obvious that a handgun or a rifle is going to destroy the eye. So instead, I figured I would focus on the three type of guns that we see most often in the clinic, and that's stuff that children have. And it's usually either a BB gun injury, airsoft injury, or a paintball gun. And let's see what kind of damage they can do. So let's begin with the BB gun. This is the classic Red Ryder BB gun produced by Daisy. It's been out forever. It's in many popular Christmas movies. This gun shoots a small pellet at 350 feet per second, which is relatively fast. Here I am cocking it. A single cock is all it takes. And the BB comes out the end, styrofoam head, to give you an idea of how this works. Now, the danger with BB guns are that the pellet itself is made out of steel. It's a non-compressible steel covered by another alloy metal on top of it. But because it's steel, it doesn't really deform. So when it hits something, it doesn't crush. It immediately bounces off. So you see a lot of ricochet injuries, and that's the danger of the BB gun. That's a little bit different than a pellet gun. A pellet or an air gun is something that you can pump up very high. And they shoot at like 1,000 feet per second, which is incredibly quick. They use pellets instead of BBs, which is usually a soft metal like lead that compresses, has a flange and more aerodynamic shape. That flange expands as it goes down the barrel, engages the rifling of the barrel, so it spins on the way out, much more accurate. And here's the classic Diablo shape, and you can see that it crushes. This crushing is good because it doesn't ricochet as much. The downside, of course, is just the sheer speed at which these pellets come out. So to put things in perspective, a handgun shoots at about 1,000 feet per second as well. So this is about the same as a handgun. A rifle, though, something a hunter would use, is about 3,000 feet per second. So it's not quite as bad as that, but that's an air gun. Our next contender is a paintball. Paintball was invented in the early 70s as a way for the logging industry and forestry to mark trees that were hard to get to. And so here I am marking a couple of trees. This is the modern air paintball gun. It has several parts, usually a compressed cylinder of CO2 air that pumps air into the barrel itself. On top, that round thing is it's a hopper, and that's where the paintballs go in. You load them through the top, they drop down into the barrel, and then the compressed air blows it out the end. Face mask is crucial with this instrument, and also something for the mouth so you don't break teeth if this thing hits you. That's a plug that you use during tournament play so people know that it's on safety. And let's shoot this head, and we'll see what kind of effect we get in paintball. You got to cover the mouth, otherwise you'll break teeth with this thing, and that's why that mask looks that way. But that's the paintball gun. Of course, if it hits the eye, some significant trauma, right? The paintball itself is relatively heavy, especially compared to a BB, and it's filled with a non-toxic paint that doesn't seem to really cause much problem. Okay. Interesting. The thing with the paintball is that this is the first gun that's meant to be shot at people, right? And interesting, this young man appears to be relatively resistant to paintball injuries. Maybe it's the hair, I don't know. But so that's a big difference. This is meant to be shot at people. Airsoft is our final contender. Airsoft was also invented in the 70s, Hong Kong, China, because of a ban on firearm ownage. They come in different styles, a CO2-powered handgun, for example, which is kind of nice because you can kind of hold it gangster style, which is, anyway, it's useful. Anyway, there's also the spring-loaded guns, which are pretty accurate. But the most impressive type of airsoft is probably the electric one that can pump out a lot of pellets at a very rapid rate, as you can see here. Just quite incredible. No. All right, where was I going with this? I don't know. Okay, back to this. Oh, there we go. That's what. Let's see if this young man's not quite as resistant to the airsoft gun, as you can tell. But we love him. And now, we have 3 different guns. But how do we judge how dangerous these guns are relative to each other as far as the eye? And one method we could do is we could calculate the kinetic energy. How much energy is traveling in that projectile when it hits the eye, and how much is transmitted to the eye? And we can calculate this relatively easy. It's a simple equation. Energy equals the mass, how heavy that little pellet is, times the velocity, how fast it's going, squared. Instead of looking at equations, now let's just measure these things. So if you take 100 BBs and you measure them on a gram scale, 100 comes out to 34 grams, so each BB weighs 0.34 grams. 10 paintballs comes out to, what, 30 grams? So each paintball is 3 grams. That's like 10 times heavier than a BB. Okay. Airsoft come in different weights. 0.12 is what most starters use, but the most popular weight is 0.2 grams. So actually about half the weight of a steel BB is what these little plastic things are. And if we plug these into our equation, we see a couple of things. The first one is that a BB gun gives about 2 joules. An airsoft is about half that. So that kind of makes sense. Airsoft has always been touted as being much safer than a BB gun, and it probably is. The paintball gun, though, a tremendous amount of kinetic energy. 15 joules is 10 times higher for the most part than those other weapons. And finally, the pellet gun, just because it goes so fast, it has a lot of energy as well. But let's not look at the equation. Let's actually do an experiment. This is called a ballistic pendulum. It's a block of nylon. You shoot from the side, and it pushes this little scale, and using that, you can kind of calculate how much kinetic energy is given. So we'll start by shooting it with a BB gun, and we'll see how far this thing moves. Shoot at the end, and that's what, about 12.5 degrees, something like that? Okay. Let's repeat that. We'll use our airsoft. Let's set it to single shot, and we'll see what type of energy is given. Okay, about 6.5 or 6, so about half. That's pretty consistent with our equation from before. But let's finally end with our paintball, and we'll see what that does. It blows it off. It doesn't even work. The ballistic pendulum's not even made to measure something that high, and it looks like we knocked our scale off. And so that paintball really does transmit a lot of kinetic energy. But you know, energy is not everything. The more important thing is penetration. After all, a bow and arrow and a baseball, fast pitch, may have the same kinetic energy, but one is more traumatic when it hits the head than the other. Same thing with a nail. A single nail can break a balloon extremely easy. But if you take 100 nails and then try to break your balloon, it's much more challenging. So it's not so much force, but how much force that area is being transmitted over. And 100 nails, it's hard to break this, right? So that's why if you get hit with a water balloon, it doesn't usually cause traumatic injury, but if you hit with a little rock, it can cause major issues. They may weigh the same, but there is a difference. So penetration is important. But rather than do equations again, let's just go ahead and just do some penetration testing. We'll start with our trusty aluminum can, and we'll start with the BB gun. And a hole through the front of the front of the can, and it comes out the back. Didn't move the can much, but sure penetrated really, really well. Let's try the airsoft. We'll see how it does. I'll do a single shot. It looks like it bounced off. Let's check. Yep. Dented the can, but the airsoft didn't penetrate either side either. That's pretty good. So something about that soft plastic airsoft and the lower joules is a good thing. Let's try our paintball gun. We'll see what happens now. Knocks it off. Did it penetrate, though? Well, it crushed it like a hammer, but it actually didn't go through. So airsoft, maybe it's not that dangerous. Okay. Good penetration testing, but we need something to simulate the eye. Let's try some tomatoes. We'll see what happens when we shoot them. We'll start with a BB, goes right through it, barely moves it, but shot out the back. Airsoft goes in, but doesn't come out. But if you set it to automatic, it can really destroy this tomato very quickly. Let's try our paintball gun. Glancing blow, sorry. Let's try it again. Well, it went in, it didn't come out the back, but it knocked it off the crate, so a lot of energy was transmitted. But you know what? We need a more accurate simulation of the human eye to see how dangerous these things are. So let's just take a pig eye and see what happens. We'll start with a BB gun, and we'll shoot it in the eye and see what happens. So here it comes. Pretty heinous, right? Did you guys miss that? Let's do it. Let's do it again. Let's do it again. Ah, okay. Did you guys miss that? Let's do it in slow motion. Okay, here it comes. Ah, heinous. Yeah, I'm sorry. It's a graphic demonstration, but BB guns penetrate really well. Let's try the airsoft. We'll see what happens. Single shot, Terrible corneal abrasion, holy moly, but it didn't penetrate. That's interesting. Even if I throw it on automatic at high rates, it doesn't go through. So, yeah. So airsoft really is a little bit safer. Not a lot of damage, but it's safer. Let's try our paintball gun. It completely destroys that eye. It's like hitting it with a hammer. It didn't penetrate as much as just explode the eye. So the paintball truly is a dangerous projectile to get hit in the eye with. And this seems to be consistent with my findings in the clinic. This is a young man hit with an airsoft, caused a hyphema, didn't penetrate, but a lot of internal ocular damage. He's at risk for developing glaucoma down the road from angle recession. BB guns, high rate of penetration. Paintball, a high rate of ruptured globe. But fortunately, we don't see these as often. I'll stress, though, that most of these injuries don't occur people playing tournament paintball and tournament airsoft. Most of these are accidents at home, kids messing with their guns in a room with a friend. They get hit at point-blank range, just like we saw here, but some significant damage. Our take-home point, though, is that paintball truly is a very dangerous weapon if used improperly. Our next topic, chemical eye injuries. And by chemicals, I'm talking usually about acids and bases. And so when I say acids, acetic acid, sulfuric acid, battery acid. And when I talk about bases, I mean things like bleach and oven and drain cleaner. And which one of these is most dangerous? We're always taught that bases are more dangerous to the eye than acids. And yet, why is that? And is that really true or not? I mean, that's one of those little factoids you remember. Well, I thought I could do an experiment just to see which one really is more dangerous. So what I have here is sulfuric acid, battery acid, and I'm pouring this into a beaker that's filled with table sugar. And what you'll see here is that it reacts with the table sugar, and you get a very exothermic reaction. It produces heat. It burns and burns that sugar. You can think of this as tissue. And it produces carbon. And this carbon is just sort of the leftover remnants. It's like a crust. And this is what happens with acids. When acids hit skin, they destroy skin, but they create coagulation necrosis, and you get almost like a crust, an Eschar, that protects it from penetrating deeper and deeper, so it's somewhat self-limiting. So acids, terrible damage, but in theory are somewhat limited because of that effect. This is a little bit different than bases. Bases are extremely caustic, and they denature proteins, they break down cell walls, but they don't create this crust, so they go deeper and they go deeper into the skin, and they keep creating damage until that reaction is completed. This is just an example. This is obviously not truly a base, but just to kind of give you an idea of the type of damage that bases can cause. But once again, this is theoretical, right? I'm just telling you that bases are worse and they do this stuff, but we need to do some type of experiment to prove this to ourselves in a little bit more graphic way. And so what I have here is two glasses. And the glass on the right, I'm going to pour concentrated sulfuric acid, extremely powerful acid, battery acid essentially. In the left glass, I'm going to put lye, basically sodium hydroxide to make soap out of it. So this is a high concentrated base on the left side. So acid on the right, base on the left. And I took some pig eyes, put them on wires, and we'll dip them into these solutions, and we're going to see what happens. And after a minute, you can see it's starting to burn, crisp on the outside, but give it a couple more minutes. And the base goes deeper and deeper on the left, and it's just kind of liquefying that, while the right just kind of burns to a crust, but doesn't go deeper. Let's give it a couple more minutes and see what happens. Well, we're getting a little bit of an exothermic reaction here. The base is getting a lot hotter. Admittedly, that has a lot to do with the water, but the base is dangerous. And after a couple of minutes, it falls off the wire. The eye is barely recognizable as an eye on that left side. So bases truly do cause significant damage. It's interesting that the lens, which is what you're seeing there, with the black uveal tissue, that's the retina and the choroid back there, survived this. But bases truly cause a lot of issues here. These are two patients that have been hit with chemicals in the eye. One has a red eye on the left and one has a white eye on the right. But which one is worse? Which is the worst injury? Well, red eye is a good thing after a chemical injury because, yes, the eye is irritated. Sure, the conjunctival blood vessels are dilated, but at least they're there. When you have a white eye, that's when you get nervous because that means you've cooked off the conjunctival vessels. And anytime you see a cloudy cornea after a chemical injury, it's a very ominous sign. If it's bad enough, the cornea might scar. It may never recover. They might require a corneal transplant. Unfortunately, these chemical injuries, they don't do real well with corneal transplants. A lot of the supporting cells at the limbus that produce epithelium, they're just cooked off. They're not working right. And so in these patients, repeated corneal failures, then they might require some type of prosthetic cornea. And this is that Capro. It's a little plastic cornea that's in there. I obviously don't do this type of surgery. This is the realm of the cornea surgeon, but these things are no fun. But if the alternative is no vision, then yes, it's worth it. But it's a lifetime of maintenance to keep these things healthy. Our take-home point here, though, as I think I've adequately demonstrated, is that bases really are very bad. All right, our next topic is light damage. This is called a Crookes Radiometer. It's a little device that was invented, I don't know, 50, 80, 100 years ago. But it's a partial vacuum light bulb that has these little veins of white and black panels. And the theory behind it originally was that light was absorbed by the black surface and bounced off the white, and it kind of proved the photon energy. It's like a solar mill, so to speak. The actual theory is a little bit different than this, and how this works. It has to do with temperature and air movements inside this thing. But it does demonstrate one thing, and that is that light can transmit energy, and that energy can create, in this case, motion, but also heat. Now, this is pretty obvious to any kid who has a magnifying glass and a ready supply of ants. And so I thought, well, maybe we could burn some eyes with a magnifying glass, but you know what? It's pretty childish to be using a small magnifying glass for this purpose. So instead, I got a very large magnifying glass. This is a Fresnel lens. It's pulled off a projection TV. I got it here on a frame. But this lens is basically the same thing as a small magnifying glass, just much, much larger. We're going to start by burning some paper in here. We'll see how fast it burns. Holding it under. Pretty quick, right? Almost instantaneous. Measuring this temperature from this little device, it gets up to about 1,500 to 2,000 degrees Fahrenheit. So extremely hot. A lot of energy can be. I'm not a big fan of animal testing, but I have no big problems with vegetable testing. So this is Darth Tater. And don't worry, folks. Darth Tater, he's the spud of evil. But we'll see how he does under the heat as well. You can see he catches fire almost instantly as well. So a lot of energy can be collected by a lens system. Eyes didn't do so well there. Finally, we'll do an aluminum cam. The melting point of aluminum is something like 1,200 degrees Fahrenheit. But once again, this melts relatively quickly. So a lens really can focus a lot of energy to a very small spot, which is pretty obvious here. Now the eye is the same thing. It's orders of magnitude smaller, but it's the same system. Fortunately, we don't see that many solar injuries from the sun because people don't look at the sun. But this can occur during surgery. Prolonged eye surgery where the eye is stuck in one position for a prolonged period of time, you can have solar damage from that. We don't see it as much now with modern surgical techniques, but certainly with prolonged retinal surgery or complicated surgery, this is something that's been seen in the past. And I've seen a couple patients with this, so relatively rare. The big question, of course, is laser light. People are always worried about lasers. And laser light is coherent light. It's all the same wavelength, extremely intense in one spot. But we're always asked, if I get shot by a laser at the checkout line at the store or a laser pointer in a crowd like this, am I going to have damage inside the eye? Well, probably not. There's been some studies looking at this effect, and what these researchers did was they took people who were scheduled for enucleation. They had like a melanoma that had to come out, the eye had to come out. So they said, well, let us shoot a laser in your eye for like 15 minutes and hold it at the same spot. And they've done that, and after they enucleated the eye, they looked at it under the microscope, and they do see some histological changes. But think about it, 15 minutes, the same spot in the retina, what's the chance of that happening? I would argue that if you stared at a reflection of the sun off someone's mirror for 15 minutes, you'd probably have some changes as well. So I think overall, consumer laser pointers are relatively safe. Now this is different than this one. This is a very powerful laser I imported from Hong Kong, barely made it through customs. Most laser pointers have a power of 5 milliwatts. This one's 1,000 milliwatts, so it's about 200 times faster than your average laser. I bought it originally because I really needed a way to pop balloons, specifically lines of balloons in a straight line. And so this laser is very good at that specific task. So pretty cool, huh? I had to turn it off pretty fast because it's starting to burn the blanket back there. But a very powerful laser. Now, I can't shoot the retinas on these pig eyes that I ordered because the cornea is just too cloudy, but I did want to sort of demonstrate that lasers really can create damage inside the eye. So we'll just shoot at the cornea and see what happens. We'll give it a couple minutes. You can see it burning away there. I had to put a special filter on my camera so I didn't blow out the sensor. And you can see that there's a burn on this cornea. Imagine that in the retina. So in these industrial lasers, these high-powered things, really can be quite dangerous. But who has those things? Come on. So our take-home point here, though, is that light, relatively safe, and especially laser pointers, they're relatively safe. I don't think they're anything to worry about. Our final topic, explosive eye injuries. After all, the title of this lecture is The Exploding Eye, right? So explosives. Does anyone know what this is? Yeah, looks kind of like an M80 that you hear about. Yeah. Don't worry, folks. This is a special effect. Look how proud of myself I am. Watch this. Huh? Yeah, okay. Anyway, this isn't truly an M80. An M80 was an explosive device invented by the military to simulate artillery fire during training exercises, but it created so many injuries. during the 50s, 60s, essentially, that they end up banning the thing. You know this isn't a true M80 because the wick is coming out the side. M80 is supposed to come out right immediately out the side, not the end. So anyway, these devices, even though they don't have nearly as much gunpowder as they used to, can still create some significant damage, especially if held in the hand. But it's when you close a container around an explosive, that's when you have the true damage. So if you close the hand, this is how you lose fingers. Let's see how this clay hand did. So a lot of damage. But I am an eye doctor, I'm not a hand doctor, so let's see what happens when we do this to the eye. So once again, we'll take our pig eyes and we'll try our Black Cat Firecracker. Caused some damage, but didn't perforate or anything. Let's check it, the old plier test. Yeah, looks pretty good. All right. Let's try enclosing this with a hand and see if it's going to break. Now, does anyone here think it's going to rupture this time? Looks like it will, right? Okay, let's check our hypothesis. Longer fuse this time. Wait for it. Wait for it. There we go. And let's see what type of damage we have now. Well, it's pretty burnt up, that's for darn sure, but is it ruptured? I don't know. It doesn't look like it is. All right. Let's try this one more time. Do we think it's going to break now? I mean, come on. All right, let's try it. All right. So did it rupture? I have no idea because this thing flew off my garage. I don't know where it is. It could be anywhere. Well, one day I'll be walking through there barefoot and I'll find it. But so I haven't the foggiest idea. But you're probably wondering, what's the point? I mean, this is a lot of fun, but like, who holds a firecracker up to their eye and lets it explode? That is rare. But what I do see occasionally is a bottle rocket hit the eye. Bottle rockets can be quite dangerous because they fly at high speed, so you can get a projectile injury. They explode near the eye and get a shrapnel injury. And one of the first injuries I saw as a new resident was a child who got hit in the eye with a bottle rocket. Fortunately, I found this one on the ground. And unfortunately, the thing had not ruptured either. And so, gosh, I was getting a little depressed at this point. I mean, this eye's not exploding, but I am not willing to build a bomb in my garage to do this purpose. So instead, what I did was I just threw it in some vise, and we'll just see what happens if we vise it, right? Yeah. And there is a purpose to this other than the gross factor. Because explosions cause compressive injuries, and that creates blunt trauma. And so we're going to create a blunt trauma here just by compressing this eye until it pops. And when the eye ruptures, it tends to rupture at 2 points. It either ruptures at the limbus, which is easy to see. It's quite obvious. The iris is usually hanging out of the eye, and so you take them to surgery. But the other place that these eyes tend to rupture is right at the insertion of the muscles onto the eye itself. Now, the eye has a thickness. The scleral wall is about 1 millimeter. But right where the muscles insert, the thickness is about a third of that. It's a third of a millimeter. I don't know why. You'd think it'd be thicker there. I mean, muscles are attaching to that spot, but it is. And so you're always worried about a rupture underneath that muscle. So if you have an injury like this, someone comes in with some type of blunt trauma, you're like, holy moly, I think it's a ruptured globe, but I can't tell because the limbus is okay. Well, you're stuck taking them to the surgery, cutting back that conjunctival tissue, and exploring under those muscles to find a rupture and repair it. If the rupture is further back behind the eye, well, you can't repair those. I mean, you can't pull the eye out and sew it up together without causing significant expulsion problems, but exploding eyes. Our take-home point here is that bottle rockets are relatively dangerous. You guys can do that already, didn't you? Now, in summary, we have learned many things. We've learned that the eye is relatively protected from heat, but can become damaged. We have learned that paintball in particular is especially dangerous to the eyeball. We have learned that bases truly are more dangerous than acids. We've learned that lasers are relatively safe unless you get these high-powered ones. And finally, that the eye is not resistant to explosions. But I hope you found this interesting. And I caution you not to try any of these experiments at home, as I almost hurt myself many times. But I'd like to thank you for your time today. Thanks.